Alrighty then, so we just established, the signs, what they mean in context regarding speed, and I gave a few examples. Okay, so now it's time to look at our sign diagrams and work out when the signs are the same. Yeah, that's why sign diagrams are really good, because you can just, interpolate, as I've been doing here. Okay, so let's go through the process then. Well, we have our velocity, we have our acceleration, and again we want to see when the speed is increasing, so the signs are going to be the same. And that whiteboard marker isn't very good. Maybe if I find my old red one, maybe this one will work. Okay, so let's have a look. We have a positive sign there and a negative sign there, and is that what we want? No, because the signs are not the same. So we don't care about that initial interval there. However, after t equals 2, we have negative, and we still have negative down here, so the signs are the same for that interval. When we go through this, we have a negative for velocity, then we have a positive for acceleration. We don't want that either. And then lastly, we have a positive, and then we have a positive left over. So we do want that, because that's good, because the signs are the same. So, the object's getting faster, speed is increasing. Okay, so now that we've gone through that, it's time to represent that. So let's see. When t is less than 2, we have a negative and a positive, so that's bad. But then starting at t equals 2, the signs are the same. So we have 2, and then we have, we put t in the middle because we show the lower end of the spectrum, the lower end of that range, and then we show the upper end. And the signs stop being the same when t equals 4, because that's when the acceleration becomes positive. Awesome, so we got t less than or equal to 2 less than or equal to t, and then we have less than or equal to 4. It's a range. It's between 2 and 4 where the signs are the same, where the speed is increasing. And that's in terms of seconds. So again, sort of picture that in your mind. Okay, an object started, and then after 2 seconds the speed's increasing, and the speed will increase until it gets to 4 seconds. Okay, and now we interpolate this range, 4 to 6. Signs are different, not what we want, but then we see positive and positive, signs are the same, t is greater than 6. And that's when the speed is increasing, when the signs are the same, and we've just evaluated that off of our little sign diagram pair there. Okay, so we've been able to do that question. Again, get your head around what that means. See the end of last episode if you're still a tad confused. But again, it should hopefully make a bit of sense in context. Okay, so now we've done that, let's have a look at another question. And the very next question asks us to draw a motion diagram. And a motion diagram, again, just is not really something that's based on time, but it's based on position. So, how's the object moving? When is the object reversing? Things like that. So if we draw a motion diagram for this, we need to think, okay, what's happening between the intervals? So, we'll have the origin somewhere in the middle, because, it could go to the left of the origin for a bit. But let's think about what's happening within the first stage there. Now we know that at t equals 0, it's going to start at the origin, and we know that it's heading in this direction, right? Okay, cool. We know that it's going to be heading in the positive direction because we found those initial conditions. It's almost like this investigation was scaffolded so you can build upon the knowledge. And by almost, I mean definitely. Okay. So now, because of that, we realise that it's going to change direction at t equals 2. Excellent. However, this is not a time scalar, because you can't have negative time for 1. But for 2, it's showing us what's actually happening to the object. So we need to work out where it's going to be at t equals 2. We know it's going to change direction there, so we know it's going to head off here, it's going to get to some point, and it's going to go back the other way. But we need to know where that point is so it turns around. Now, how do we work that out? Well, again, we know there's a stationary point on the s function because this is its derivative, so that translates to a stationary point on the actual function. S of t, again, the displacement function. Oops, didn't mean to put a prime in there. But what we can do is we can just plug 2 into that. It's literally that simple. We're finding the displacement at time equals 2 seconds into this motion of the object. So I know particle again, as I said, or maybe a bus or a car or a rabbit, anything. So we find the S of 2, and we find a whiteboard marker that actually works. I need to go through these. The problem is they die so quickly when I use them. Probably because I overuse them. So we have 1/3 of 2 to the power of 3. Again, I'm just plugging 2 into its original displacement function. Take 4 lots of 2 squared plus 12 lots of 2. Simplify this down. So we have 1/3 of 8. Take 4 lots of 4. So I'm going to simplify it down to 16 in there. Plus 24. And then we're going to get its displacement. We're going to know where this thing is at time equals 2. And voila, we can just multiply across. So 1 times 8 is going to be equal to 8. And it's going to be 8 on 3. Because imagine that this is, 8 on 1. Because there's an imaginary denominator of 1 on any whole number. Hopefully you sort of understand why, and you understand the basics of fractions. You just multiply across the top. The numerators, you get the product of them. And then you get the product of the denominators as well. 8 on 3. Take 16 plus 24. And now, you could work that out if you really wanted to on pencil and paper, or if you're like me and you're a little bit lazy and it's getting a little bit late at night, you can accidentally grab across the actual camera and make everything black out for a second there. Sorry about that. And, calculate it in here because it's embarrassing if you make a mistake. Hopefully I've gone through it correctly now. But we should get 10 2/3. And that should be the point at which it actually reverses direction. So that's where it should be after 2 seconds. And let's just do the logical think check on that. Okay, this is what I like to do to make sure I'm not stuffing up big time. Because stuffing up big time is bad news. Okay, so let's think about it. The object. We worked out in the first video, the very first part, a long time ago now, but we worked out that it was moving at 8 meters per second to the right, correct? Yep, okay. Well, if it's moving at 8 meters per second to the right constantly, then it's going to end up at 16 meters after 2 seconds, okay? That makes sense? But then we've got to remember that there was a deceleration force too. And that deceleration force was causing it to slow down as well. And that deceleration force should have been, something along the lines of, and I'm not sure if I actually worked it out here, but anyway, getting back to it, it does make sort of sense in context. So I'm just going to continue, and I'm pretty sure I'm right. But that means that we have a point here, 10 2/3, at which the motion turns around. That's t equals 2. And it's going to go back the other way. Now we need to know what happens where it turns next. So where does it turn next? Let's see. Velocity shows us where it turns because it represents stationary points on the displacement function. Hopefully you get an appreciation of what that is. If you don't understand what that is, just try to. Just think about it for a moment. Think about the derivative. When the derivative equals 0, what happens to the original function? And how is that so relevant for when we're actually trying to find reverses direction? If you get that into your mind and you understand why and it just clicks, then a lot of this stuff will just click. Because you've got an understanding of motion, movement, a very awesome thing. Okay, so now let's find what happens when it's at the next stationary point of 6. So we find the S of 6. Alrighty. And that whiteboard marker's satisfactory, so let's just keep going on with this. So we just replace... No, it's not satisfactory anymore. I just think I should seriously stick with red for the moment being. And we go and we change our values as appropriate across the duration of the equation, and then, we just rub them out, hopefully. Okay, and now what we can do is we can just multiply across, so we work out what 6 to the power of 3 is for our displacement. So 6 raised to the power of 3 is going to be 216. So we have 1/3 of 216. Now I'm just going to go ahead and see, can I divide 216 by 3? Pretty sure I can. Yes, 72. So, because we got 72 there, I'm just going to put that straight in. Again, you can sort of follow my logic there. And then we have 4 times 36, and 4 times 36 is 144. Okay, and then what we're going to do is it's 12 times 6, which is going to be 72, but I'm just going to check it anyway. And yes, we get plus 72 there. So 72 plus 72 is going to be equal to, and we've got 144. 144, take 144. 0. Well, what does this mean in our context? Well, in terms of our motion diagram, it means at t equals 6, it's going to be back at the origin. It's an interesting thought. But yes, it's pretty cool to consider it's going to be back at the origin, but we've been able to prove it by looking at displacement at that given time, and again, we know it reverses direction, so it must reverse direction at the origin. Okay, and now what we do is we work out that, okay, it's just going to continue increasing, and let's work it out for when s equals 8. Let's say that it asks us, what is the total distance travelled of the object in the first 8 seconds of motion? And if it asks us something like that, again, we just need to add those up. So we put 8 in there, so we get 1/3 of 8 to the power of 3, then we have 8 squared here, and then we have 8 there, and what we do is we just go through and we plug it into our calculator, and I'll just plug in the whole thing, so we have 1 divided by 3, so we've got 1/3, lots of 8 to the power of 3, and then we go take 4, lots of, and I'll simplify that on the fly to 64, plus 12, lots of 8. And voila, well, isn't that interesting? We actually get 10 2/3. Does this make sense? Well, yes, technically it does make sense, because think about it. It's just like the object returning to the origin again, and the velocity acceleration acting on it again. Because again, here it has a velocity of 0, so it's like it's starting off fresh and it's accelerating, and at t equals 8, it's going to be back to where it was before, at 10.667. 10 2/3. So now, the question might be, how far does the object travel within its first 8 seconds of motion? And in order to get this, it's quite simple, it's not too difficult. We just need to do some simple math. Okay, well, it's going to be 10 2/3, right? That's where it goes in the first few seconds. Then it goes back, and that's another 10 2/3. Make sense? Yep. Got one 10 2/3, another 10 2/3. So, it's travelled that far, and then we've got another 10 2/3. So all it really is 10 2/3 times by 3. And let's see if we can actually work this out. So what we can do is we can convert this into an improper fraction. Pretty easy to do, not too difficult. So we go 10 times 3, that makes 30, and it's going to be 30 plus 2, because we've got 2 over 3 there. So it's 32 over 3, times by 3 over 1. And 32 times by 3 should leave us just under 100 with 96. And then it's 96 divided by 3, and 96 divided by 3 is approximately, is equal to 32. Again, sort of makes sense there, because we start with 32, we divide it by 3, and then we times it by 3, so of course it's going to be 32 in the end. Could have just taken a shortcut there, but doesn't matter. So, again, we can't just work out the displacement at time equals 8, because the displacement at time equals 8 is 10.667. It actually travels there and back. The displacement is a vector quantity. It's saying, oh, okay, so you moved from the origin to there, pretty much, over the first seconds. How far are you from where you started? That's all it asks. It doesn't ask how far you've actually gone. Think about it. You could walk around your entire building 2 times back to where you started. And technically, you're at the same position as where you started, so your displacement would be 0. Again, similar sort of thing here, but it means that therefore the object, and again, we had meters per second before, so we know that this is in meters, but the object has travelled 32 meters in 8 seconds. Something like that, just a statement. And again, there we go. We have a little look at motion. We understand some of the concepts of motion. Hopefully you get it. Have any questions, please ask me, but that's all for now. Bye.